Lesson 11.3.1 Multiple Representations of Exponential Models. In Module 11, we have seen how linear functions and linear inequalities can be used to solve real-world problems. Linear functions have the key property of a constant rate of change. This means that every increase in x of 1 unit causes the exact same change in y. This is a good review of what you've just seen in the first half of this module. This is really all that linear functions are about. But now, in this lesson, we will re-examine exponential functions and identify their key properties. Comparing investments. Imagine that you want to invest some money. You are considering two investments. Investment 1, Bascom Blackwell offers an investment that doubles your money every 4 years. Investment 2, Cassandra Cooper offers an investment that increases 18.92% each year. The amount of money you plan to invest is between $100 and $1,000. This initial amount of money will remain in either investment 1 or investment 2 for 8 years. Decide on an initial amount that you will invest and write the initial amount on the line below. I'm going to choose that we will invest $500. Number 1, to compare the two investments, write the initial amount you chose for year 0 in the table below. This is on the next page. Year 0 is the first row, so I'm going to put $500 as the initial investment for both investments. Complete the table using the initial amount you selected as your starting point. Calculate the value of each investment over the 8-year period. You do not need to find a value for the shaded part of the table. Instead, find the value of the investment 1 at years 0, 4, and 8, and then find the value of investment 2 every year from 0 to 8. Be sure to round your answers to 3 decimal places. Hint, even though your initial amount may be different from your classmates, the steps to find the values of the investments will be the same. This is saying if you wanted to do this on your own, you could choose your own initial investment just to see how this works. So remember, investment 1 says that the investment doubles every 4 years. So the column for investment 1 is actually pretty simple to complete. You have a beginning investment of $500. 4 years later would be the row that has 4. It would double. So 500 doubled just means $500 times 2, which is $1,000. And then another 4 years after that would be year 8. We would double again. Remember, it's doubling every 4 years, so this is doubling from what it was at year 4. So that means at year 8, it's 2 times 1,000, which is 2,000. So investment 1 doubles every 4 years, and this is what we would get. $500 to start with, then $1,000 after 4 years, and then $2,000 after 8 years. So now let's work with investment 2. And we start with $500, and we need to remember that for investment 2, the investment increases 18.92% each year. So this is reminding us of also how percentages work. So if we wanted to find how much this investment is worth after 1 year, investment 2, after 1 year, its worth is $500 plus 18.92% of $500. You've done this before when you've worked with taxes. You find a percent of a purchase and then you add that tax amount to the cost. You've also done this if you've ever tipped in a restaurant. You have a percentage of the cost and then you add that to the bill. It's the same idea here. We're finding a percentage of our investment, 18.92% of $500, and then we're adding that to $500. So remember, 18.92% is the same thing as 0.1892. So I'm really going to take 500 and I'm going to add 0.1892 times 500. So 0.1892 times 500, that's 94.6, and then when you add that to 500, you get 594.6. So that becomes the worth on year 1, 594.6. So now to find after the second year, I now have to start with 594.6, and it's going to increase from that by 18.92%. So investment 2, year 2, I have to start with 594.6, and then I have to add 18.92% of 594.6, but that's just the same thing as 0.1892 times 594.6. So 594.6 times 0.1892. That gives me 112.49832, and then I'll add that to 594.6, and then they say round this to 3 decimal places, and I get 707.098. If you're wondering why are they having us round to 3 decimal places if this is dollars and cents, we're trying to keep as much information along this whole process because we want to make sure that we're getting great estimates all the way down to year 8. So now, at this point, we might remember something that we did in Module 4, where if we're adding a multiple of a number, and then that number relates to where we started with, this actually has a simpler way of being done. What I wrote here, 594.6 plus 0.1892 times 594.6, is the same process as 500 times 0.1892 times 500. So for year 3, I'm going to start with 707.098. But instead of adding to 0.1892 times 707.098, I'm actually just going to multiply that number by 1.1892. You might be reminded of something you did in Module 4 where you had a concept of B and then how that related with the number 1. So here I've got 1.1892. I'm going to multiply these. 707.098 times 1.1892. And I get 840.881. So going back to my column, 840.881. Now to see how this works with what we did before, let's just see if this same process could have been done at the very beginning. Take your calculator, take 500, multiply by 1.1892. And what do you get? You get 594.6. So this is the same as 500 times 1.1892. And then the same thing happens with year 2. You could take 594.6 times 1.1892, and you get 707.098. So what you can see is that the way that this works, we're not adding the same amount every year like we would have done with a linear function. We're multiplying by the same number to go from one year to the next. So let's try this out for year 4. So year 4, I'm going to take where we left off with in year 3, 840.881, and I'm going to multiply by 1.1892. So 840.881 times 1.1892. And I get 999.976. Okay. So now that we see that there's an easier way to find all of these, let's go from year 4 to year 5. I'm just going to take 999.976 and multiply by 1.1892. And I get 1189.171. So I'm just going to remind us that every time we want to go from one row to the next, I just need to multiply by 1.1892. And I can do that to always go from one row to the next. So we started off slowly by reminding ourselves how percentages work, but we did see this same concept in Module 4. So that's where we're getting that all we have to do is just multiply by 1.1892. Where does the 1 come from? The 1 comes from the one value that you had to start with. And then you're adding a 0.1892 times the value that you started with. 1 plus 1.892 is the 1.1892 that we have here that we're multiplying. So for year 6, for investment 2, 1189.171 times 1.1892. And what we get is 1414.162. And then for year 7, I'll take 1414.162 and then multiply by 1.1892. And I get 1681.721, and then 1681.721 times 1.1892, and I get 1999.903 at the end of 8 years. So now let's take a look at what we have in this table in relationship to number 2. Number 2 asks, what do you notice about the value of each investment at the end of the 8 years? So the end of 8 years for investment 1 is $2,000. The end of 8 years for investment 2, if we were to write that as dollars and cents, it would be $1,999.90. So, are they pretty close to each other? They're only off by 10 cents, so they are about the same. So now for number 3, let's focus on investment 2. Can investment 2 be modeled with a linear function? Does it increase by the same amount in each year? What this means by does it increase, you need to think in terms of dollars. Can I take 1 year's amount, add a dollar amount, and then add that same dollar amount for the next year? The answer to that is no. When you look at investment 2, at the very beginning we had $500. What did we add? We added $94.60. But now what did we add going from year 1 to year 2? That was over $100. So we didn't add the same amount. So no, we do not add the same dollar amount. Each year. As we keep going along, you can see that the amount of dollars that this investment goes up by each year starts to get into the $200 range. Look at from year 6 to year 7. It goes from 1,400 and so dollars up to 1,600 and so dollars. All right, so we don't have the same dollar amount being added every year. This is again why it's not a linear function. This is why we're starting to look at what's called an exponential function. So now number 4, develop a formula for the value of investment 2 over time. Let B represent the value of investment 2 and let T represent the number of years since the investment began. Hint, the formula must include the initial amount of the investment and the yearly growth rate. Here's where we see a phrase that we saw in Module 4. So the idea of growth rate relates to what we call the growth factor, and that's what we saw in an exponential function. So we're going to have an exponential function where B is the value of the investment. That's going to be equal to the initial investment or initial amount times our growth factor raised to a power. T. T is the power that is going to be varying because we will have varying years for this. What's the initial amount? We already know. It's $500. What's the growth factor? We also already know that. I kept multiplying by 1.1892. And then T is an exponent. So to see why this is correct, take out your calculator and let's just find an example. Let's say when T is equal to 5. B, the value of the investment 2, will be equal to 500 times 1.1892 raised to the power of 5. Remember to use powers on your calculator. You have to use the button that looks like an upside down V, and then you type in the number 5. So 500 times parentheses 1.1892, close the parenthesis, then raised to the power of 5, and notice that we get approximately 1189.172. And what did we have before in our column for year 5? We had 1189.171. Why is the third decimal place slightly different? Because in what we did in the table, we had 1, 2, 3, 4, 5 steps of rounding. Whereas in the calculation that we just did here, as my example, we did it in one shot. So we get a little bit of a better amount as far as our estimation. Okay, but our answer for number 4 is this formula that we had. I was just pointing out an example off to the side. So now next steps. In Module 4, we learned about exponential curves. An exponential curve has the general form y is equal to capital A times a number b raised to the power x. That's exactly the same form as what we just had in number 4. The variables a and b in this exponential function have the following key properties. First, capital A is the y-intercept of the curve. It is the value when x is equal to 0, and it's also called the initial value. We had a y-intercept and an initial value with linear functions. You also find that when x is equal to 0, but here we have a different form of our model. If b is greater than 1, b is called the growth factor. That's what I just called it up in number 4. If b is between 0 and 1, b is called the decay factor. We won't ever have negative values of b, and we'll also never find that b is equal to 0 or 1. These are the only values for b that we have in exponential functions. We can use this general form to determine an exponential function for real-world situations based on written descriptions. Situations that use exponential functions often involve percent increases or decreases. To translate a written description to an exponential function, we must identify the initial value and the growth factor or decay factor. Creating an exponential function using a growth factor and an initial amount. In the previous example, investment 2 grew by 18.92% each year. This is an example of exponential growth. The percent increase each year is 18.92%. This means that each year the value of the investment increases by 18.92% of the value it had at the beginning of that year. The growth factor is equal to 100% plus the percent increase, which is 100% plus 18.92%, which is the same thing as 118.92%, and that's where we get the 1.1892. Each year, the value of the investment is multiplied by 1.1892. Recall that we convert the percent to a decimal for arithmetic purposes like multiplication. To do this, we move the decimal left 2 places. So this whole paragraph, this explains what we were doing on the previous page. If you weren't sure about what we were doing on the previous page, here's one paragraph that explains it all again for you. So now, for example, suppose the initial amount of your investment is $300 instead of $500. If the yearly growth factor is 1.1892, the investment will increase by 18.92% in the first year. At the end of the first year, 1 year since the beginning, the investment will be worth 300 times 1.1892, and that's equal to 356.76. This is shown in the second row of Table A below. So you can see this on the next page. And again, if you want to check that this is right, start off with the slow way that we did on the previous page. Take $300, add 0.1892 times $300. When you just do the multiplication first, 0.1892 times 300, you get 56.76. And then when you add 300 plus 56.76, you get 356.76. So again, this is showing you that we can do it the old way, but now we have a faster way of doing these things using the exponential functions. So now in the second year, the investment will again increase by 18.92%. At the end of the second year, 2 years since the beginning, the investment will now be worth 356.76. That was again the amount that they started the second year with, times 1.1892, and that's $424.26. Rather than using the value after 1 year, we will instead use the initial value 300 to find the value of the investment at the end of the second year. How would they do this? We multiply the initial amount 300 by the growth factor twice. So you multiply by 1.1892 and then you multiply it again by 1.1892. This and more is shown in the third row of the table below. So if we take a look at the third row of the table, you can see that's right here. Year 2, here's what they were talking about, 300 times 1.1892 times 1.1892. But instead of just writing all of that multiplication, we can speed that up with an exponent. That's the same thing as 300 times 1.1892 raised to the power of 2. And then that gives us 424.26 as the value of the investment. Finally, on the last paragraph of the previous page, we can use this pattern to determine the value of the investment at the end of any year. To determine the value of the investment after T years, we must multiply the initial amount by the growth factor T times. This generalization leads to the exponential function capital A is equal to 300 times 1.1892 raised to the T power, where capital A in this form is the amount of the investment T years since the beginning. This is shown in the last row of the table. So here you can see in the table, we've got rows for years since the beginning, 0, 1, 2, 3. That's helping us recognize the pattern, but then we generalize it. The value of the investment at T years would be 300 times 1.1892 raised to the t power. The previous problem was an example of exponential growth. In this next example, we will work on creating an exponential function with a decay factor. We will work on calculating percent decrease over time. Whenever you take medication, you are instructed to take a specific amount of medication every number of hours. The reason for this is that the amount of medicine in our bloodstream decreases exponentially over time. Suppose the amount of drug in a person's bloodstream decreases by 30% each hour. Another way to think about this is that you have a certain amount of the drug in your system at the beginning of the hour. By the end of the hour, there will be 30% less of that drug in your body. In this example, the decay factor is equal to, this time, 100% minus the percent decrease because we are subtracting something, which is equal to 100% minus 30%, which is 70% or 0.70. That is our decay factor. Each hour, 30% of the drug is lost, and that also means 70% of the drug remains in the system. If the initial amount of the drug is 6 milligrams and the hourly decay factor is 0.70, the function for the exponential model is capital A for the amount of the drug that's left is equal to 6 times 0.70 raised to the h power, where h represents the number of hours since the drug was administered. Notice here the variable names A, B, T, H. It really doesn't matter as long as you just specify what it is that you're talking about. A is the amount of the drug in the body in this particular example, and H is the number of hours since the drug was first taken. Use your knowledge of growth and decay factors to write exponential functions for the following situations. Number 5, cobalt-60 is a radioactive element which decays at 14% per year. If a lab has 35 grams of cobalt-60 on January 1st, 2003, write a function for the amount capital A of cobalt-60 the lab has t years after January 1st, 2003. So notice we have decay. So what do we have to find? Decay factor. The way that we can do this is just like we saw previously, right up above. We take 100%, we subtract the 14% that it decays every year. That leaves us with 86%, which is the same thing as 0.86. We also need the initial amount. Which that was given to us as 35 grams when this started on January 1st, 2003. And now we want to write the function, a mathematical function for the amount, capital A, that is left t years after January 1st, 2003. So again, this is our initial amount, 35, times our factor, in this case a decay factor, 0.86, raised to the, they're using t for the number of years, power. And that's it. So now let's look at number 6 on the next page. Statisticians have estimated that the world population increases by about 1.2% each year. In September of 2012, the world population was estimated to be approximately 7.04 billion people. Write a function for the estimated world population, capital P, t years after September 2012. So now we have population increase. So we have population growth, so we'd be looking for a growth factor. So in this case, the growth factor, just like we did earlier in the lesson, that would be 100% plus, since we're increasing, 1.2%. That's the same thing as 101.2%, which is the same thing as 1.012 as our factor. And then the initial amount, that's the 7.04 billion people. And as long as we understand that population capital P is measured in billions, then we can say that P is equal to 7.04 times our growth factor, 1.012, raised to our power, again, T is the variable that we are using for time. Number 7. Lake Merritt has been chemically polluted by the farms in its watershed and is now in the process of being cleaned. When the cleanup of Lake Merritt started on June 1st, 2011, the concentration of chemical pollutant was 810 microliters per milliliter of water. The mathematical model for this cleanup says that for each month after cleanup started, the amount of the pollutant in the lake is 3/4 of the amount of the previous month. Write the function for the concentration of the pollutant in the water, capital P, at T months after June 1st, 2011. Now this one's a little bit more difficult than the previous examples. Here, if we want to find whether we have growth or decay, we need to think intuitively, are they cleaning this up? Yes. Do they expect that the pollutant should go away? Yes. So we probably have decay here. We wouldn't want the opposite. We wouldn't want the pollutants to be growing. So it's pretty clear that we have decay. Okay, so now, are we given an amount that the pollutant goes down as a percent? No. We are told that the amount of the pollutant in the lake is 3/4 of the amount of the previous month. And to think about what that means, I want to go back to the previous page and just notice what we had in the paragraphs before we started number 5. When we go back to the third paragraph, where we talked about the decay factor of 70%, notice this says each hour 30% of the drug is lost, but 70% of the drug remains. That's telling you how much is left. So now go back to number 7. It doesn't say that this goes down by 3/4. It says that the amount of the pollutant in the lake is 3/4 of what you had started with in the previous month. So that's 3/4 that is left. So 3/4 is remaining. So our decay factor is actually that 3/4. And if you take 3 and divide by 4, or if you just think about how much money do you have when you have 3/4 in your hand, that's 0.75. So notice we didn't have to do any subtraction in this problem. Not every problem is going to involve addition and subtraction just because you saw it before. There's other ways of considering these exponential functions. So our exponential function has a decay factor of 0.75, and then our initial amount, that was the 810 microliters. So the function for the concentration of the pollutant in the water, that's using capital P. That's 810 as the initial amount times the decay factor 0.75 raised to the T power. Number 8, the function capital P equal to 150,000 times 1.035 raised to the T power describes the population of a town, capital P, at T years after 2000. Write a description of the exponential growth or exponential decay process of the town's population. Think about the starting population of the town and how fast the population is increasing or decreasing. So at least we can say the population started, what was the initial amount? That's the 150,000, with 150,000 people when? the year 2000, 20 years ago. Okay, so that's our first sentence that we can talk about the initial value. Now, is the population increasing or decreasing? Well, take a look at the number that's in the parentheses, 1.035. That's exponential growth. So the growth factor is 1.035. So now, how would we describe how fast the population is increasing in this case? Because we have growth. Well, now we're going to do the opposite of what we did in the previous examples. When we had to use addition or subtraction to start with a rate and get a factor, now we're going to undo that. So here, I want to just remind us of something we saw in Module 4. Recall, rate is equal to b minus 1, where b stands for our growth or decay factor. That's something that we did back in Module 4. So notice that our rate is equal to our growth factor of 1.035 minus 1, which is 0.035. And if we write that as a percent, that's 3.5%. So that means the population increases at a rate of 3.5% each year. So that describes the growth of the population in this town. The population increases at a rate of 3.5% each year. Number 9, the function capital V equal to 26,000 times 0.85 to the t power describes the value capital V of a new vehicle t years after it is purchased from a car dealership. Write a description of the exponential growth or decay process of the vehicle's value. This is very similar to the previous example, but now we're looking at decay. How do we know that this is decay? Take a look at the factor, 0.85. That is telling us that we have a decay factor. So just like number 8, I'm going to first start with what was the initial value? That's the 26,000. So the initial value of what? Of the vehicle. Of the new vehicle. This is the idea of putting things into context. Was $26,000. And then the decay factor is 0.85. How did we use this back in Module 4? The exact same thing that I wrote down in number 8. Recall, rate is equal to b minus 1, which in this case is 0.85 minus 1. And when you subtract that, 0.85 minus 1, that says negative 0.15. Now the negative, what is that implying here? That's implying decrease in value, decay. So this says negative 15%, which how do I interpret that? The value of the vehicle decreases at a rate of 15% each, and T stands for years, each year. How come I didn't write negative 15%? Because I wrote the word decreases. I don't need to write the negative because of that. That's just how we interpret it. A negative percent means that we are decreasing by that percent. So now number 10. Describe in words a specific example of something that grows exponentially. Think about something that increases by the same percent every hour or month or year. You are currently living in one of the greatest examples of exponential functions. Just think about why we are all not in class right now. A virus. That is something that grows exponentially. If you look up things about a virus, there is something called an R0 or an R0 number. That tells you how many people one person can infect if they have the virus. And with the current virus that we have, that number is greater than 1, which implies that each person can infect more than one person with the virus, which is giving an idea of exponential growth. The virus starts to spread less often if that R0 number goes below 1. Number 11 says exchange your description with a partner and then find the function of your partner's written description. So here, think about other things that can grow exponentially. There's all kinds of examples that you can think of. Now, number 12, describe in words a specific example of something that decays exponentially. We've seen a few examples: worth of something, radioactive material, pollution. There's all kinds of other things that decay exponentially. Try to see if you can look up some things that decay exponentially. Talk about that with your classmates. Number 13 then just asks you to exchange those ideas with each other and think about that. But what we are going to end with is some other ideas of exponential growth and decay that relate to some other concepts, one of them called doubling time and another one in a little bit called half-time or half-life. So first, doubling time. At the beginning of this lesson, we saw two different descriptions for the same exponential process. The first description, doubling every 4 years, provides information about the amount of time required for the investment to double. This is an example of doubling time. The second description, increases by 18.92% each year, provides information on the yearly growth rate. We will now find an exponential function for investment 1 when the only information we are given is the doubling time. Suppose investment 1 started with an initial amount of $1,000. Let's examine how investment 1 changes over a 4-year period. So first of all, let n be the number of 4-year periods. Pay attention to that. N is the number of 4-year periods. After the beginning of the investment, we will double the amount during each of those years or those periods. The table below illustrates the growth of the investment over several 4-year periods. So notice here, the first column says years since the beginning, T. And notice those numbers that they have in that column are 0, 4, 8, 12. They're increasing by an amount of 4. In the next column over, it says number of 4-year periods since the beginning. Here we have n. So at the beginning, 0. But the next row says 1 because we have one amount of 4 years. Then the next number says 2 because we have two amounts of 4 years. 8 is the same thing as 2 times 4. And then we have 3 because 12 is the same thing as 3 times 4. So with any number n, meaning number of 4-year periods, the amount of years is just 4 times that, 4n. And then for the investments, that's the third column. If we start with $1,000, at the end of the first 4-year period, that would be doubling, so 1,000 times 2. That's the same thing as 1,000 times 2 to the first. That's $2,000. And then for the next time period, we would start with 1,000 again, but now we would multiply by 2 for the first 4 years, and then another 2 for the next 4 years. That's the same thing as 1,000 times 2 to the second. And then this is not, as they have there, that's a typo. This is $4,000. And then at the end of the third 4-year period, so that would be 12 years later, we start with 1,000, then multiply by 2 once, then 2 for a second time, and then 2 for a third time. That would be 1,000 times 2 to the third. which is the same thing as 1,000 times 8, which is 8,000. So then the amount in the investment at the very bottom, that's the same thing as 1,000 times 2 to the n. Just notice how they are using the number n, just like they did with the 1, 2, and the 3. 1 was the power, then 2 was the power, and then 3 was the power. So the same thing happens with n as the power. The last row of the table shows that the amount of money, capital A, in investment 1 after n 4-year periods since the beginning of the investment is the same thing as capital A equal to 1,000 times 2 to the n. So you can see how we can get an exponential function even from that concept of doubling. So now, number 14. Use the pattern between n and t columns of table B. T was the first column, n was the second column, to help you write an equation that shows the relationship between n and t. So, what we can see is that if you have a number n, how many 4-year periods, you multiply it by 4 and you get the number of years, t. So 4 times n is the same thing as t. N stands for the number of 4-year periods and t stands for time. You could also think that by our knowledge of what we saw with functions before, we could also say that n is the same thing as t divided by 4. Because if the number of years was 12 years, 12 divided by 4 is 3, that was 3 4-year periods. So then number 15, use the equation relating n and t from our previous question, number 14, to replace n with t in the function for a, which means I would like to take this, n is equal to t divided by 4, and put that in for n in my previous formula. So a is equal to 1,000 times 2 to the n becomes capital A is equal to 1,000 times 2 raised to the t over 4 power. And that becomes our formula where we can now find the amount for any time t, where now t is measured in years. Turning the page, number 16, fill in the table below by finding the value of the investment 1 at each year specified in the table. Round your answers to 1 decimal place. So now we're going to pick up where we left off using that formula, a equal 1,000 times 2 raised to the t divided by 4. And we're going to replace t with the numbers that we see in the column, 0, 1, 2, 4, 6, and 8. So maybe grab a piece of scratch paper if you need to. Have a calculator definitely. First, we're going to start with t equal to 0. And let's just remember that when t is equal to 0, that's our initial value. So if you were to do this using the formula, you would have a equal to 1,000 times 2 raised to the power of 0 over 4. 0 divided by 4 is 0. So this is the same thing as 1,000 times 2 raised to the 0 power. Anything raised to the 0 power is 1, so this becomes 1,000 times 1, or just 1,000. So that works with our formula. Now let's do this for t equal to 1. So t equal to 1, a would be 1,000 times 2 raised to the 1/4. And I would suggest trying to do some of these things using some scratch room. 1 divided by 4, just plug that into your calculator. That's 1/4, or 0.25. So this becomes 1,000 times 2 raised to the 0.25 power, which means you can type 1,000 times parentheses 2, close the parentheses, then use that upside down V symbol for raising a power, 0.25, press enter, and notice what you get, 1189.207. And they say round your answers to one decimal place, so I'm just going to write 1189.2. 1189.2. Now for t equal to 2, I'm going to go off to the left where I've got some more room, t equal to 2. This will be a is equal to 1,000 times 2 raised to the 2 over 4. But 2 divided by 4 is just 0.5. So that's the same thing now as 1,000 raised to the 2 raised to the power 0.5. 1,000 times parentheses 2, close the parentheses, raised to the power 0.5, and you get 1414.2. Okay, so now how about t equal to 4? Now keep in mind, every 4 years, we should have a doubling of the investment from where we started with. So if t equals 0, we have $1,000. Then at t equal 4, that's 4 years later, we should have 2,000. Let's see if that is true from our formula. When I plug in t equal to 4, I get a is equal to 1,000 times 2 raised to the power 4 divided by 4. But 4 divided by 4 is just 1, so this is 1,000 times 2 to the first. That's the same thing as 1,000 times 2. And you'll see if you plug that into your calculator, that's what you get, 2,000. Okay, so this is showing us that this whole doubling exercise that we were doing, writing an exponential function, it's giving us the same results we saw earlier. So now let's do t equals 6. I'm going to use the top margin for that. A is equal to 1,000 times 2 raised to the 6 divided by 4. 6 divided by 4 is the same thing as 1.5. So I get 1,000 times 2 raised to the power 1.5, and I get 2828.4. And then if you were to use t equal to 8, that's going to give you the same result we saw before. That's 2 periods of 4 years after the beginning, so we should expect that we have 1,000 times 2 times another 2. That gives us 4,000. Also notice what happens from year 2 to year 6. That's 4 years later, right? 6 is 4 years after year 2. Look at the amounts. You started with 1414.2 in year 2, and it doubled in year 6, 2828.4. So this is true even for other time periods besides 0 and 4 and 8. As long as it's every 4 years, we'll still see the doubling effect. All right, now number 17, graph the amount of the investment on the coordinate plane below, which means we're going to take the years that we have. Those are our horizontal values, so these are the t values down there. And then we're also going to match those up with the amount of the investment. Those are the a values. So for example, at t equal to 0, we had $1,000. That gives us a point on the vertical axis corresponding with 0 as the horizontal number and then going up to 1,000. And I put a little dot. For 1 year later, the amount is 1189.2. That's pretty close to 1,200. So I get another dot. Then for year 2, 1414.2. So that's going to be a little bit above 1,400. And then at year 4, we didn't do a year 3, so we're skipping now over to year 4. The amount was $2,000. And then year 6, we said 2828, so a little bit above 2,800. And then year 8, we said 4,000. And notice this is not quite a straight line. There is a curving to this. You can see that it's got a little bit of a curve implying the exponential growth. Number 18, use the graph to estimate how long it will take for the investment to reach $3,000. It will help if you connect the points with a smooth curve. So we've already connected the points with a smooth curve. $3,000 is here, so let's just find where 3,000 intersects with the graph, and it looks like somewhere between 6 and 7 years. Okay, so between 6 and 7 years. When we are given the doubling time of an exponential process and the initial amount, we can create an exponential function to model what is happening. In the following examples, we will use an exponential function to determine the percent increase that occurs during each unit of time. A biology research scientist is growing bacteria in a petri dish in a lab. His model says that under these conditions, the bacteria will double every 3 days. Part A, if the culture starts with 400 bacteria, write a function for the number of bacteria, capital N standing for that, after T days. Use your answer to number 15 to help you with this question. So let's go back to number 15. Remember in number 15 we wrote down an equation where you could use n as the number of time periods, or you could use t to stand for the number of years. Remember that in that problem that we were looking at, we had doubling every 4 years. Now in number 19, doubles every 3 days. So just like we would have seen in number 15, we could have said something like t, the number of years, is 3 times the number of periods it takes to double, or you could say that n is equal to t divided by 3. Just like in number 15, we said n was equal to t divided by 4 because it took 4 years to double. Here we're saying 3, as in days, it takes to double. So t is here standing for days instead of years, but the concept of how we can use the 3 is still the same. So now number of bacteria, capital N, is equal to initial amount, 400, times, since we're doubling, 2, and then now the power is t divided by 3. Notice how this form is exactly the same as what we saw in number 15, just different initial amount and different applications. So we're not using money and we're not using years, we're using bacteria count and days. Part B, use your function to find the number of bacteria after 6 days. Is your function correct? Think about how many times the bacteria should double in 6 days. So first of all, we can do this intuitively. If we start with 400, 3 days later, there would be 2 times 400. And then 3 days later after that, we would have 2 times again. So 6 days is 2 doubling periods. So we should have 400 times 2, which is 1,600. If we were to use our formula, we would say n is equal to 400 times 2 raised to the t is equal to 6 here, 6 divided by 3, but 6 divided by 3 is 2, so this is 400 times 2 raised to the second power. That's just 400 times 4, that's also 1,600. So this is, again, just giving us a way to verify that our formula was correct. We know the amount of bacteria doubles every 3 days, but how much does it increase each day? To answer this question, we can calculate the percent increase. The percent increase during the first day can be calculated using the following formula. Percent increase is equal to bacteria count at day 1 minus bacteria count at day 0 divided by the bacteria count at day 0. So part C, calculate the percent increase from day 0 to day 1. We know the bacteria count at day 0 was 400, but we don't know the bacteria count at day 1. So let's find that first. Day 1 means that t is equal to 1. So n is equal to 400 times 2 raised to the 1/3 power. So now you can take 1 and divide by 3. Notice you'll get a 0.333333. We actually want to use a lot of that. So then what I'm going to write next is 400 times 2 raised to the 0.333333, just so I can get a good estimate from this. 400 times parentheses 2 raised to the power 0.333333. And what I get is 503.968. So now I'm going to find the percent increase. The percent increase would be the amount at day 1, which is 503.968, minus the amount at day 0, which was 400, and then divide by 400. First, let me do the subtraction. 503.968 minus 400 is 103.968. And then we're going to divide that by 400. And what you're finding with this is the amount that was changed is the number went up by 103.968. And we're finding what percent of the original amount is that. So 103.968 divided by 400, you get 0.25992. That's approximately 0.260, which is 26%. So it went up by 26%. Now let's do the same thing from day 1 to day 2. Now this means that we need to find the day 2 amount. So day 2, n is equal to 400 times 2 raised to the 2/3 power. 2/3 is the same thing as 0.666666. So then I will multiply 400 times parentheses 2 raised to the 0.666666. And I get 634.960. So now the percent increase from day 1 to day 2. This isn't going to use day 1 and day 0 like we did before. Now I have to use day 1 and day 2. And what you want to think of this is the percent increase is the new amount, that's the day 2 amount, minus where you started, that was the day 1 amount, because we're only going from day 1 to day 2, and then divided by what you started with, which was the day 1 amount. So this gives me 634.960 minus 503.968 divided by what we started with in day 1, 503.968. So first 634.960 minus 503.968. That gives me a difference of 130.992. And then divide that by 503.968. And notice you get 0.2599, which again rounds to 0.260, which is the same thing as 26%. So notice the percent increase from day 0 to day 1, 26%. The percent increase from day 1 to day 2, also 26%. So now how about part E? In case we're not convinced, calculate the percent increase from day 4 to day 5. So now you have to find the day 5 amount and the day 4 amount, which means plug in 5 to your formula for T, plug in 4 for your formula for T, get those amounts. What you're going to get in part E is the percent increase will be the day 5 amount minus the day 4 amount divided by the day 4 amount. The day 5 amount you'll find out to be 1269.921. The day 4 amount will be 1007.937. And then you're going to divide by the day 4 amount, 1007.937. Do the subtraction and then the division. It should be no surprise. You're going to get 26% again. So part F, what do you notice about the percent increase from one day to the next? It is always 26%. So now part G. Use the percent increase to write an exponential function for the amount of bacteria A in the Petri dish after T days. Write the function using the growth factor instead of the doubling time. So if the growth rate is 26%, remember that the factor would be 100%, as we learned earlier in this lesson, plus 26%, which is 126%, or 1.26, which means that our exponential function is our initial value. So first of all, n for number of bacteria. Well, I guess actually they say that should be a, because we're writing a slightly different function. A equal to our initial value, 400, times the growth factor, 1.26, raised to the t power. So what we've done here is connect this idea of doubling time with what we saw earlier with exponential functions. And now the final concept we'll see with exponential functions, half-life. Number 20, cesium-137 is a radioactive chemical element that is released into the environment after nuclear tests and nuclear disasters. It has a half-life of 30 years. This means that every 30 years, the amount of cesium-137 will decrease by half. The Macintosh lab had 8 grams of cesium-137 on January 1st, 1975. The amount of cesium-137, capital A, remaining can be described by the exponential function capital A for amount is equal to 8 times 1/2 raised to the t divided by 30 power, where t is the number of years since January 1st, 1975. Part A. How much did the Macintosh lab have on January 1st, 1992? So first, let's recognize some things about the function. Notice that the 8 is in front of the parentheses. This should remind you of the initial value, just like we saw used before with doubling. Then you have inside the parentheses 1/2 instead of 2. Why is it 1/2? Because we are finding half-life. That's what we're talking about here. So we are cutting something in half. And then also notice the exponent is t divided by 30. Remember in the previous examples we had t divided by 3 or t divided by 4, where the bottom of the fraction was just telling us how long it took for something to double. Now 30 tells us how long it takes for something to be in half. So we're using the same concept as we saw before. Half-life and doubling, they're very related in just the form of the exponential function. So keeping that in mind, part A, how much did the Macintosh lab have on January 1st, 1992? Well, first of all, we need to know what is the value of t. T, as we were told, is the number of years since January 1st, 1975. T is the number of years since January 1st, 1975. So how many years is that? Take 1992, subtract 1975, and you get 17. 17 years since then. So then capital A is 8 times 1/2 raised to the 17 over 30 power. Now, if you want to enter all of this into your calculator at once, you can certainly do it. I would recommend doing this. 8 times parentheses. Instead of 1/2, use 0.5. That's the same thing as 1/2. And then for 17 over 30, I'm going to write the caret symbol, or the upside down V symbol. And then after that, I'm going to write another set of parentheses where I have 17 divided by 30. That way I can do this all at once. 8 times parentheses 0.5, close the parenthesis, then hit the power button, the upside down V button, make a new parenthesis, 17 divided by 30, close that parenthesis, and then press enter. And what you should get is approximately 5.401. That's the amount that the Macintosh lab had on January 1st, 1992. And we should make sure that we say grams here, since that's how they're measuring the amount. We're not using dollars anymore. So part B, when would this cesium-137 have been reduced to 6 grams? Well, it's already down to 5.401 in 1992, so it probably has to be sometime before that. So we're going to complete this table to see if we can answer the question. First, we start with t equal to 0. What's the initial amount? Again, we already said that was 8. And instead of writing the g for all of these numbers that we'll do down here, I'm going to say that A, the amount, is measured in grams. Just write it at the top of the table, just so I know. So now t equal to 2. This is again just getting us used to using the formula. So for t equal to 2, you're going to have A is equal to 8 times 0.5 raised to the power of 2 divided by 30. So 8 times parentheses 0.5 raised to the power of 2 divided by 30. Don't forget your parentheses around that 2 divided by 30. And you should get 7.639. And then t equal to 4. Let's do the next one. A is equal to 8 times 0.5 raised to the power of 4 divided by 30. And when you type that in, you get 7.294. And then let's do t equal to 6. That gives me A is equal to 8 times 0.5 raised to the 6 divided by 30. And I get 6.964. And we can keep doing this 8, 10, 12, 14, 16, 18, 20. And you're going to see this go down. And the next one, t equal 8, you're going to get 6.650. For t equal to 10, you will get 6.350. For t equal to 12, 6.063. We're almost there. And now t equal to 14, 5.789. So we can see that we've crossed over somewhere between 12 and 14. So just finishing the table, t equal to 16, 5.528. T equal to 18, 5.278, and then finally t equal to 20, 5.040. I'll let you do all the work on your own just to check along with the answers that I have here. But it looks like after 12 years, that's when it's going to finally be reduced to 6 grams. You can see that 12 years later it's at 6.063, so maybe just a little bit after that. So just after 12 years, we have 6 grams. So what year is that? Because they ask when. 12 years after 1975. Is 1975 plus 12 years. That's 1987. That's the answer. They also ask us to complete a graph. This is just like what we did before. I'm just going to have some dots representing the points that we had in the table. So remember, at t equals 0, we had 8. At t equal to 2, I had 7.639. That's a little bit more than 7.5. At t equal to 4, 7.294. That's about halfway between 7 and 7.5. At 6, 6.964, that's just about 7. 8, 6.650, just above 6.5. 10, 6.350, that's just below 6.5. 12, 6.063, that's just right above 6. T equal 14, 5.789. That was about halfway between 5.5 and 6. 16, 5.528, so just about at 5.5. 18, 5.278. And then finally 20, 5.04. You can see that this is decreasing as we go from left to right. In part C, it says, as you can see from the graph, cesium-137 decreased each year. What is the percent decrease each year? So this is going to be similar to what we saw in the previous example when we had percent increase. So to find this, we can choose any 2 consecutive years. So how about we just say percent decrease. Let's pick year 2 amount minus year 1, and then divide that by year 1. Year 2 amount we already got from the table on our previous page. The amount in year 2 was 7.639. We need the year 1 amount, so for t equal to 1, the amount would be A equal to 8 times 0.5 raised to the 1 divided by 30. Plugging that into our calculator, we'll get 7.817. So that becomes the year 1 amount that I'll use in my formula here, 7.817. And we'll also divide by 7.817. So at first, let's do the difference. 7.639 minus 7.817. You get a negative number, but remember, that's okay because we're talking about percent decrease. That's what the negative is meaning. And so really what we want to focus on is 0.178, how much it went down by, what percentage of what we started with, 7.817, is that? So now negative 0.178 divided by 7.817, that gives us negative 0.022. Converting that to a percent is negative 2.2%. So what is the percent decrease? Oh, that should actually be a 0.023. Negative 2.3%. So what is the percent decrease? Is 2.3% each day. And remember, the negative is implied with the word decrease. So now part D. Write the exponential function for the amount of cesium-137 remaining after t years using the decay factor. Hint, calculate the decay factor using the percent decrease. So I need to start with 100%, and I need to decrease by the 2.3% that it goes down every day. That gives me 97.7%, or 0.977. That's the decay factor. So then our exponential function is A for the amount that's left, equal the initial amount, 8 grams, times the decay factor, 0.977, raised to the t power. And now finally, number 21. What information about an exponential process do you need in order to create a function for an exponential model? Just think of those things that I needed to create my functions in all of the examples we had today. We need an initial value, and then we need the number that goes in the parentheses. That's a factor. So we need a growth or decay factor. And then to end this lesson, the word for this lesson is factor.